So, we were discussing the kings and jogs that are formed after intersection. So, we had taken an example where we said that Berger vector 1 is 0 0 1 and assuming edge dislocation B 2 equal to 0 1 0 for edge dislocation, and these are the final information that we obtained regarding the steps. Now, let us see if instead of edge dislocation, if we had a screw dislocation, would anything be different? And the answer would be no. So, whether you start for this particular information, all we needed was Berger vector, and we do not need to know whether it is edge dislocation or a screw dislocation. So, this could as well be edge or screw. And even in the edge dislocation, we never worried about what is the line vector. In fact, for this particular one, if the line vector is along 0 0 1, then this is similar to case 1, where the step is along the line vector and therefore, it is not observable, but we are not worried about that. We are trying to show is that whether the starting dislocation is edge or screw does not matter, and all that matters is the Berger vector, because that is what forms the step in magnitude as well as in vector. So, now this is for a simple case. Now, I have always said that in the real system the dislocations are a little bit more complicated. So, let us talk about a screw dislocation of Berger vector 1 B 1 equal to 1 1 1, and it intersects with another screw dislocation of Berger vector 2 equal to 1 bar 1 0. Actually, this is 1 1 0 and this is 1 bar 1 0. So, we have one screw dislocation whose Berger vector is 1 1 0 and the another screw dislocation whose Berger vector is 1 bar 1 0. So, in this particular case you can realize that this is the case for FCC. In FCC we have this kind of system. So, this is a realistic system where we see a dislocation with a system like this. Now, what I want to do is to get the information about the step dislocation. So, the magnitude of step dislocation is how much? It is equal to 1 1 0 is equal to root 2 a. Sorry, this should be the magnitude will come out same, but I should have written 1 bar 1 0, because it has to be equal to B 2, S 1 is equal to B 2 in magnitude. Now, the vector direction of S 1, that is equal to 1 bar 1 0. Over here what we have for the second case, S 2 magnitude we take, for this we take the magnitude of 1 1 0 and then this again comes out to root 2 a, and the vector of S 2 is equal to 1 1 0. So, here again we see that what we obtained are with respect to the other dislocation. Now, in this particular case I had given that the initial dislocation was screw dislocation. So, here the initial line vector is equal to u 1 equal to 1 1 0. Here the initial line vector is equal to 1 bar 1 0, and in this we are getting a step which is 1 bar 1 0, and this and the Berger vector for this is still the same, which is so what do we see here? Over here this line vector is perpendicular to the Berger vector, which means line vector is perpendicular to Berger vector would mean what? Edge dislocation. Here also what we see 1 1 0 is perpendicular to 1 bar 1 0. If you take a dot product it comes out 0, and therefore, again here also it is a edge dislocation. Now, here again if you look at it, I had given extra information screw dislocation of Berger vector B 1 and B 2. Did I ever use this information screw dislocation? I have given the value u 1 here and u 2 here, but I am never using it. So, again this information is extraneous, it is not required at this stage. If we just want what is the character, what is the step size, magnitude, it's all these information, these can be obtained alone from the Berger vector, and that is what we see here. So, with that we move on to another aspect regarding dislocation motion. So, you can realize that whenever dislocation is moving, it moves in response to stresses being applied, and when there is stress being applied, plastic deformation is taking place. So, there must be strain. So, you can say the outcome of dislocation motion is that some strain is produced. So, motion of dislocation produces strain, and we can, if there is a strain, then there will also be strain rate. So, here we will look at a simple model which is which has been simplified to a great extent to be able to derive a relation for strain. So, what is this simple model? We assume that we have a rectangular block where all the dislocations are aligned along one direction, although we will assume that there are positive as well as negative. So, there is a shear stress acting like this. So, this is the length L along which we will assume all the dislocation lines are located. This is height h, and we will say call this width as distance t. Now, if we will assume, okay, here we have to show that there are some dislocations, there can be positive, and we will, for the sake of simplicity, I will just put 4 dislocations over here. So, these are long dislocation line which terminate from end to end. Okay. Now, under the effect of these stress, what will happen? All these positive dislocations will move like this, negative dislocations will move like this, and what will be the final shape, what you will get would be something like in the cross section. This is how it will look like. So, a shear stress is being applied. So, we want to calculate a shear strain. So, for that first let us see what is the total displacement along this direction d. Now, if a dislocation moves through a hole of this length d, then what will be the displacement? Displacement will be equal to 1 Berger vector equal to 1 b. Now, let us say that one particular ith dislocation moves through only xi distance. So, ith dislocation moves through a fraction of it, which is shown by xi by d. Therefore, it will produce a displacement equal to b xi by d. Now, if there are n dislocations, so total displacement due to n dislocations, this can be given by d equal to summation b xi by d, where I goes from 1 to n. Over here we can say that b and d are common or basically constant. So, it becomes b over d and xi I equal to 1 to n. If we were to calculate shear strain, then shear strain the stress is being applied on this surface. So, the shear strain will be displacement along this divided by h. So, shear strain would be equal to d by h, and therefore, it will become b by dh summation xi. So, this will be the shear strain that will be caused because of several dislocations that are moving inside this, and the assumption that we have taken is that all the dislocations are from end to end along this length L. Now, this density of mobile dislocations, this can be given as so here we will see two things. One, there is xi, this x summation xi can be written as actually 1 over n times x bar, where x bar is average displacement. So, if you know the average displacement of the dislocations, so we can find an approximate value of summation xi. Summation xi would be equal to n times x bar. This is simple statistics. So, summation xi can be replaced by nx bar, and let me write it here. So, if we write it in these terms, b nx bar by dh. Now, next thing that we want to know is dislocation density, which is mobile dislocation density, and over here you can see in the given context it will be equal to n is the number of dislocations and it is per length, density is number length per meter cube. So, it is per meter square quantity. So, n into L, so total length divided by the volume, which is h into L into d, which will be equal to n by h d. Meaning this term here n by h d can be replaced by, so our term epsilon can be replaced, which was written like b n by dh x bar, this can be replaced, this term can be replaced as rho m. So, we will have rho m b x bar. So, this under this configuration we have derived the relation for strain in terms of mobile dislocation density, the Berger vector, and the average displacement of the dislocation. So, if we know these three quantities, we can find out what will be the strain in the material. And what will be strain rate? If we take the derivative of this with respect to time, we can get strain rate. So, strain rate can be written as, and here what is the, on the other side what is the term that can be, for which we can take derivative of time, that is x bar, which will become v bar. So, average velocity. So, this derivation has led us to a relation on the right hand side of which are all internal quantities, and on the left side we have the external quantity, which is the, for example, in during a deformation process what the strain rate that you will apply, and because of that how the density will change or what velocity it will, the dislocations will obtain. So, we can relate the two quantities. So, it is a very useful relation. So, here we also introduce a term velocity. So, let us try to understand a little bit about velocity of dislocations. So, next what we want to look at so dislocations, as we saw, as a response of shear stress, they will move and they will move with a certain velocity. So, what is the relation of velocity with respect to shear stress? That is what we want to explore over here. So, in this not explore, but I want to show you or give you the gist of the data or information that people have obtained so far regarding the velocity. So, first and foremost, velocity is dependent not just on shear stress, but there are other factors also. So, velocity is a parameter, or velocity is a value which of the dislocation which depends on, of course, it will depend on the applied shear stress. This is the first and foremost, but this is not the only one, in meaning that not all material will experience same amount of velocity for the same amount of stress. So, what are the other factors that will depend? Purity of crystal. So, even if you talk about a pure 99.999% copper versus 99% copper, there will be difference in velocity of dislocations. Then temperature, obviously at higher temperature you would expect the dislocations to move at a faster rate. So, temperature is also a factor which will determine what will be the absolute velocity of the dislocations. And one of the other important factors, we are relating only the important factors, there can be several more. Type of dislocation. So, for example, if you look at the velocity of edge dislocation, it is known to be approximately 50 times velocity of screw dislocation. So, the type of dislocation also does make a good amount of difference to the velocity that can be obtained. Applied shear stress, now let us see what do we know about the effect of applied shear stress. So, an approximate plot can be made like this, where on the x axis you have shear stress and on the y axis you have velocity. So, usual plot, so okay, let me here first give you some approximate so velocity varies. So, usually velocity is found to vary from 10 to the power minus 11 to 10 to the power 1 meter per second, and when a shear stress in this range is applied 10 to the power minus 2 to 10 to the power minus 3. And some of the material which have been largely studied include NaCl. So, for NaCl a plot like this is seen. So, you remember, so keep in mind that over here what we have is a log scale. So, this is not a linear scale. So, in the log scale you see a linear region and there are two tails of this. This is on the higher end and this is on the lower end. Similarly, you would see something like this for a lithium fluoride. So, this is lithium fluoride, this is NaCl. Now, there are two, when you look at this velocity as a function of shear stress, there are two important aspects that need to be understood, that which happens over here. Over here what you see is that a critical stress is usually necessary. Okay, I am using the word usually because material to material the response of the material or the response of the dislocation is very different. So, a critical stress is required for dislocation movement, which is what? Which is onset of plasticity. If you are applying stress which is in the elastic regime, then of course dislocations are not generated and therefore, you would not see any dislocation movement. So, this particular minimum stress that is required in the crystals is basically representing the onset of plasticity. Another thing that you see is towards the higher end, and this is the damping force. So, at as you keep, there is a linear region, you in the log scale you keep increasing stress and velocity keeps increasing, but towards the higher side as you start approaching 10 to the power 3 shear stress mega Newton per meter square, the velocity does not increase as rapidly, and that happens because of damping phenomena. And this damping, as we will see, is represented particularly for FCC and HCP materials by a parameter. It increases. So, damping force increasingly approaches dislocation motion. So, beyond a point, as you keep increasing the shear stress, the damping force becomes increasingly large and increasingly oppose dislocation motion. So, at higher velocity you see this kind of saturation. Okay, now there are certain empirical relations people have obtained. So, let us look at some of those empirical relation which describe a relation between velocity and the shear stress, and it is usually given by so here tau is the applied shear stress resolved along the Berger vector. Tau naught is the shear stress where velocity is equal to 1 meter per second. So, this is a relative quantity. So, shear stress for velocity equal to 1 meter per second, and n is a constant. So, this n is approximately for the material, some of the materials for which it has been studied, it is approximately equal to 25 for lithium fluoride. So, that is how the shear stress influences velocity. We will look at the dislocation motion from the atomistic scale or atomistic perspective later on. Here we are just trying to give you a perspective of what are the factors that will influence velocity of the dislocation, and as you can see, as you would expect, shear stress is one of the most important one, and it does velocity does increase very rapidly with increase in shear stress. There is also effect of temperature, as we have already mentioned. So, this effect of temperature has also been captured for certain material, and what people have observed. So, if you take, so I will just write log V over here, log stress over here, then what people have observed that the linear portion, if you increase the temperature, so this direction temperature is increasing, and it is in this direction that n is decreasing. So, temperature has the largest influence on this characteristics on this parameter n, and hence influences the velocity, overall velocity of the material. But like I said earlier that the effect of stress on velocity is not same for all materials, and particularly for FCC and HCP people have observed a different kind of a little different behavior. So, for FCC and HCP it has been found that velocity is equal to a tau to the power m, where m is approximately 1 for pure metals, and so this is a quantity which does not change much m. So, for most of the FCC and HCP you would, the only thing that will change is A, and it is approximately equal to 2.5 for alloys. So, here you are also able to see a difference in the relation with purity of the material. So, for pure material m is coming out to be 1, and for pure alloys or meaning that there is a heavy alloying, then you would see 2.5, and if you are putting in just a small amount of impurities, it should be somewhere in between these two. Okay, so now we have looked at various aspects of dislocation, but one particular aspect of dislocation that we have not yet touched, which we just briefly talked about in the very beginning, is observation of dislocations. So, if you remember in the very beginning I informed you that dislocation theory was developed long before any observation was made, and the first observation, so first observation of dislocation was made in 1956. So, this was the first direct in fact any kind of observation of dislocation, and the theories, if you remember in early 30s people had developed full fledged theory of dislocation. So, 25 years since the complete theory of dislocation was developed, that first observation of dislocation was actually observed, and then people started making relation to what was actually understood previously using theories. So, what are the different methods? So, what we are trying to focus here is methods of observation. So, now you can I have already mentioned this was TM. So, what are the other methods? In fact, even in TM, so what are the different methods of observation of dislocations? In this connection, let us list out some of the important methods which are available, and the first and foremost that has been available to people is the surface methods, meaning something simple as simple as. So, these are not direct observation, indirect observation, but still some method which were available to people to be able to observe dislocation. And in fact, as I will point out later, that using this method people have been able to find out dislocation velocity, dislocation, understand behavior of the dislocation motion, etc. So, what is this surface method? Now, if you remember that in the dislocation core there is a lot of energy, and there is also, you can say, a lot of strain in the system. So, if there is a lot of strain and if you etch the material over there, what do you expect if let us say there is a dislocation which is. So, let me again as usual draw edge dislocation. So, edge dislocation which is terminating on the surface, I am drawing a surface over here and there is a core around it. So, this core, as you can expect, has high energy and it is under severe strain, there is a lot of strain in this particular region. So, now if you over edged it, what would you expect? And you would expect a preferential etching over there, and that is what people have actually observed. So, in some cases people have observed, so this kind of etched surface or on the termination, and what it represents is that there is a dislocation line below it. So, etching by rapid dissolution. In fact, etching can sometime also lead to, this is for edge dislocation, for screw dislocation it will be different, and otherwise mentioning is that not only the cylindrical kind, but you can also see the effect of facetting. So, you may see even for a edge dislocation, what you may see in some case, in many cases, in fact not some cases, because of the crystalline nature of the material, you may see this kind of faceted structure. So, you would see something like this, and what it implies is that below this is the dislocation line. So, over here it gets etched and you are able to see the end part, but if you allow it to etch for more and more time, what you would expect is that it will keep etching towards the bottom side, it will keep etching deeper and deeper and deeper, because this is a highly strained region with high energy. So, it gets preferentially etched, and you may also see screw dislocation causing steps like this. So, because of preferential etching, you may also see ledges like this, and this will be because of screw dislocation, and there is a. So, this particular method is useful when rho is less than equal to 10 to the power minus 10 per meter square. So, this is one method, and we will come back and discuss more methods of studying or observing dislocations.